Oh, we're back for another video. Hey, let's go. Last time we did uh the cool little mean standard deviation thing for binomial distributions. It was really easy. It was great. Today is a little bit more notey, and a little less mathy because we're gonna start learning about continuous random variables. So just sit back, relax, hang in there. We'll just talk about things. So we got a histogram here. It shows the vocab scores of all 7th grade students in Gary, Indiana on the ITBS. You guys ever take the ITBS? I did. ITBS. That's what I took in middle school. You guys all did like map and stuff. We took the ITBS. Anyways, enough about me. So what's the shape of this histogram? Well, it's pretty symmetric, right? I mean, it's not perfect. It doesn't have to be perfect, but, looks like a nice curve, right? Nice curve. What do we have down here? ITBS scores are given in decimals, okay? This is important. So X can take on any value between 1 to 13, okay? So this is where we're bringing in the continuous thing. So far, we've been really focused on discrete. Like you can only get 0, 1, 2, 3 of something instead of like 2.5, 2.75, 3.6159. Okay. So now we could be any value in between here. Okay. So if X is less than 6, it just means you scored less than 6 on your ITBS vocab as a 7th grader in Gary. So we can take our histogram and draw a curve through the tops of the histogram bars to get a good idea of the overall pattern of the distribution. This curve here is called a density curve. It's got some properties we're going to talk about in a second here. Jeez, excuse me. Wow, Mr. T, chill. Okay, this is called the density curve. All right. A density curve describes the probability distribution of a continuous random variable and has the following two properties. Again, if you need to pause and write these things down, feel free. I'm going to keep rolling. Here are the two properties. Number one, it's always on or above the horizontal axis, so it cannot dip below our x-axis. Okay, pretty straightforward. That makes sense. Has an area of exactly 1. This is super important. We're still dealing with probabilities here, folks. Okay, so it still has to add up to 1, like we've been saying all probability chapter. So if you calculus kids took the integral of this curve from 0 to 13 or whatever it is, 1 to 13, you'd get an integral of 1. Okay, it'd equal 1, whatever this curve is. Okay, so really important. Okay, everything under this is 1. Now you're like, oh, but these are whatever whole numbers, 8, right? But it's going to be like the number of kids in that 8 range is whatever. This is the probability this way going vertically. Okay, so it's all going to add up to 1. The probability of any event involving a continuous random variable is the area under the density curve. Okay, so if you wanted, like here, do you see they shaded less than 6? So if you could find that part of the curve under that the probability is less than 6, okay, that'd be the probability that someone scores less than 6 if you could find the area under that curve for that portion of the curve. All right, I know that's a little confusing, but stick with me. The probability distribution for a continuous random variable assigns probabilities to intervals of outcomes rather than individual outcomes. Okay, so you're gonna put all these outcomes in one interval, okay, right? And like a histogram. This is where a histogram makes more sense than when we did it Remember we were doing one with a Jeep and it's like, yeah, I mean, we'll say it's at 300 and that, this is the probability that you make $300 and then go to 450. This makes way more sense, right? I'm saying there's a group of kids that are between 6 and 6.5, basically, So we're looking at intervals of probability now. So let's say that this is, okay. So there's what's called a uniform distribution, which aren't the most interesting things in the world, but let me show you what it looks like, because these do come up if you take probability in college, which I hope you all do, and then you send Mr. T an email and you're like, Mr. T, I didn't realize like how much you taught me in class until I was in college, and I learned all this stuff that you'd already taught me, and you're the best teacher ever. And then we'll all be happy. Okay, so it's really boring. And then then you tell your professor that I said uniform distribution is really boring, and then they'll be upset at you. Okay, moving on. So let's make our density curve. So this is going to be our height. We said it has a height of 1. So we'll say height equals 1. Change color to make the density curve. And we're going, let's spell height right. Height equals 1. And then we're going to go beep, beep. There's our density curve. So our height is 1, and we're going from 0 to 1 because the area under our density curve has to be 1. So we can't go further here, because if our height is 1, then our density curve would not be 1 underneath. So let's find and interpret 0.3 to 0.7. So let's change colors again. Let's say this is 0.3. This is 0.7. Okay, so here would be our area underneath this, right? So if we have, what's this distance, right? This distance is 0.4 times our height, which is 1. Okay, so the probability that we land in between 0.3 and 0.7 is just 0.4. Seems kind of silly, doesn't it? Like, why do we have to do all this? These are, uniform distributions are actually useful, but there's a 40% chance that we land in between this. They are useful. So we don't do a ton with them, but if you see them in college, you'll use them. Let's keep on moving. We kind of get that. If you need me to explain more, let me know. Whoa, that was a double click. Okay, so here's another vocab thing. A lot of vocab in this section. The mean of a continuous random variable is the point at which its probability distribution would balance. Okay, so you can see as the book has nicely shown you, this would not balance here. It's going to tip. This is going to tip the other way. This looks nice and balanced, right? So this right here is going to be your mean. Okay, wherever that balance point is going to be your mean for your continuous random variable. All right. See what else we got. Ooh, the median. So now we're going back to mean versus median. Okay, so mean is the balance point. The median of a continuous random variable is the 50th percentile. So whatever the exactly halfway, it divides the area under the density curve exactly in half. Okay, so your 50th percentile. So think about those poor ITBS kids in Gary, Indiana. Wherever the 50th percentile is would be the median. Okay, good stuff. If the probability distribution is symmetric, then the mean and the median are the same. This is so important. The probability distribution is symmetric, the mean and median are the same. If the probability distribution is skewed, like we saw up here, this is clearly skewed right? Look at that long tail, If it's skewed right, then they're gonna be different. And we discussed way back in the day which one would be more affected, right? The mean usually is gonna go in the direction of the skew more than the median would. The median will move a bit towards the skew. But if the mean and this one is here, I'd guess the median, is like right there. It's probably a little bit more to the left. The tail, the mean goes towards the tail. All right, let's take a look at what we got under the thing. Okay, here's your example. Oh, and Mr. T, oh, look at it. He knew what was coming. What a good teacher. Okay, symmetric, they're right on. Boom, right in the middle, right dead center. Okay, but if you have a tail, long tail, the median is going to go a little bit towards the tail. True, it will. But the mean's going to go more towards the tail. So again, things are skewed. Which one should we use? Yeah, the median. Awesome. Okay, let's keep it rolling. Feel like we still got a lot to talk about. The probability distribution of a continuous random variable is shown. Identify the location of the mean and median by letter. C looks a little too nice, doesn't it? Kind of right where you would expect it if it was symmetric. So what would we say? We'd probably say B is the median. B is the median. And then A is the mean is what I would guess. Oh gosh, this is terrible. That M is just gross. And then A is the mean. Ding, 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 ding. Okay. Okay, interesting point here. We can roughly estimate the mean of a continuous random variable by I, but it's very difficult to know the standard deviation by I unless we have a very specific type of distribution. What do we think we're leading into? The big reveal. What does this shape look like, children? We talked about it earlier. Here's our ITBS scores from Gary and Deanna. We've talked about this shape before, but now we're finally gonna do it. It's a normal distribution or a bell curve. It's a bell curve. We got good old Bell in the house. It is a bell curve. Let's go. Vámonos, muchachos. Okay. A bell curve is also called a normal distribution. It has several important properties. Let's go over them now. Number one, all normal distributions are symmetric, single peaked, and bell-shaped. Good old bell curve. Again, you need to pause and write it. Feel free. Number two, the mean is located at the midpoint of the symmetric density curve and is the same as the median. Remember, I said that was going to be important when we talked about it earlier. It's because for normal distributions, your mean and median are going to be the same. Dead center. The standard deviation measures the variability, the width of a normal distribution. We'll get more into this next lesson, but we can do some cool stuff even without other stuff. Oh, we are going to do a little estimation. Okay. Basically what you want to think about for the estimation on a normal density curve or a bell curve is where it really kind of starts to turn. So it would be an inflection point if you're doing it in calculus. So if we're kind of following this curve at some point, if I kept following it, I'd go down. That's where your standard deviation is going to be. This is a little silly, but like if I'm following this curve with my pen, I would keep going down and then it'd become like that. Okay, so at some point, the graph turns and goes out and it widens, right? At that point, that's where your standard deviation is, okay? So when you feel it kind of start to change steepness, okay, change slope, that is where you're going to estimate your standard deviation is, okay? Kind of a weird method, but that's it. Okay, I think we're good. Do we kind of get that last thing one more time maybe on this one? So when you start to feel it change slope, like here, it's like, okay, we're gonna go wider. That's where you're gonna put your standard deviation at, okay? So it's kind of a weird thing, but that's how it works. Another awesome video. I hope you guys are enjoying these as much as I am. It's been fun. Adios. Hasta luego. Until next time. Signing off.